So let's summarize what we've learned today. So we explored how light beams would appear to be different to different inertial observers. And we saw two effects. One is the effect of aberration, which is the deflection of the light beam, or the direction the light beam appears to be moving relative to the direction of relative motion between observers S and S prime. So if observers S and S prime are in relative motion, let's say along the x-axis, and the light beam makes an angle theta prime as seen by S prime, and it makes an angle theta as seen by S, then we saw that there's a relationship between theta and theta prime, which is given by tan theta is sine theta over cosine theta plus beta into the square root of 1 minus beta square. Now, to be sure, in Galilean relativity as well, you expect the angle as measured by S to be different from the angle as measured by S prime. But the difference in special relativity is this prediction of this factor of square root of 1 minus beta square. So the slope as measured by S is smaller than the slope as expected in Galilean relativity by the factor of square root of 1 minus beta square. The other thing that we saw is a Doppler shift. That is, if the frequency as seen by S prime is nu prime, the frequency as seen by S would be nu, and nu would be related to nu prime through this relationship times the square root of 1 minus beta square. Again, this part over here is exactly what we expect in Galilean relativity. The square root of 1 minus beta square is something new that's only seen in special relativity. This leads to one very dramatic consequence, is that we expect a transverse Doppler shift. That is, even when the source is moving perpendicular to the direction between the source and the detector, you still see a Doppler shift. And in that case, the light appears to be redshifted. In fact, the transverse Doppler shift can be understood very simply. If the time period in the frame S prime is 1 over t prime, then the time period is t prime rather, then the time period as measured by S will be longer. It'll be t prime over or t prime times gamma would be the time period as measured by S, okay, since time would appear to be dilated in the frame S. And therefore the frequency nu prime, which is 1 over t prime, would be related to nu, which is 1 by t, as 1 over gamma times nu prime. So this transverse Doppler shift can be understood very easily just from the idea of time dilation. Now, something very important here is that there are some properties that about light that we cannot derive just by looking at the phase of the light beam. Okay, so everything that we derived today about the aberration and the Doppler shift, this had to do with assuming that the phase of the light beam at a particular space-time point as seen by all inertial observers has to be exactly the same. However, there are other properties, for example, the polarization of a light beam, and these properties would depend in more detail on how the electric and magnetic fields, which is what the light beam is composed of, how those transform or how those are seen by different inertial observers. We will discuss that effect on the polarization of light beams in a later class.